Welcome, everybody, to the final MathWorks mini-series session for 2026. We're very excited to have you here. If this is your first time joining us for a MathWorks webinar this year, we're excited to have you. Make sure to go back and check out our previous episodes. But for those of you who've been along the journey, thank you again for being a part of such an exciting series of sessions with Abhishek here from MathWorks. Tonight, we're going to be talking about how to simulate a drone taking off and landing from a moving platform. So we know, especially for our SUAS and our RobotX students that live in the world of drones, this is going to be a very exciting topic to engage in, and especially for our RobotX students who have lived in the world of getting drones to take on and off of platforms that are moving pretty regularly. This is one we highly encourage you to pay attention to. We're very excited to have Abhishek's knowledge tonight to discuss through MathWorks and all the platforms they have how to make this possible. For those of you who've been here before, you've heard this spiel, but Abhishek knows exactly what it's like to be in your position. He's been a student at one of our programs. He competed in the IGVC competition a number of years ago, and you've probably seen him around at our various competitions. He's served as a judge and exhibited on site with us. So he's a valuable part and a very valued part of our RoboNation community. So without further ado, I will pass it over to Abhishek. Thank you.
Thank you. Hello, everyone. I'm glad to join the third and final webinar for this year. Today's topic is going to be simulation of a landing UAV on a moving platform. The moving platform, in this sense, is going to be a ship, which hopefully will be very similar to what you would do at RobotX when you have to interface with your boat and a drone or any rotor aircraft. For the agenda today, we'll go over the problem statement a little bit, or try to understand what we want to achieve. And then we'll look at the dynamics modeling, because we are simulating everything. We need to get the dynamics of the drone and the ship. And then we'll see how we can detect a landing zone. And then we will look at how we can plan and control the drone so that, plan a path and control the drone so that it can land in that detected zone. Then we'll look at the simulation part and Simulink, and I want to talk a little bit about the MathWorks award that we have coming up for this year. And finally, we'll have some questions. But if you do have questions, please type it in the chat, and we'll address it as we go ahead. All right. For the problem statement, instead of typing it, I thought I would show you what we're trying to achieve. So let me play the video. You can see that there's a ship that's rocking and it's going somewhere, and then you're trying to land this drone on the ship's landing pad. And the key sensor that the drone has is a LiDAR, and you can see the point cloud on the top left. So it's going to use LiDAR to try to detect the landing zone, and then use some planning algorithms to plan a path, and then go to that landing zone. So that's going to be the problem statement, which is similar to what we had at RobotX a couple of years ago. I know some of the teams used MATLAB for it, but then we also wanted to do a simulation to show how we can do it, and probably help more teams for the upcoming RobotX challenge. So let's talk about dynamics first. There's two parts to this problem, right? There's this drone, and then you have this ship here. Right now, what I did for this webinar is have the drone modeled more in detail, and then the ship has a simple dynamics, right? It's just going to go forward, but it has some rocking motion so as to simulate how a ship would move, because we are not too concerned about the exact dynamics of the ship. The focus is more on how can the UAV plan a path, detect the landing zone, and land there. But then the good thing about Simulink is that you can always just remove this and then have a more higher fidelity simulation model for the ship as well. But coming to the drone dynamics, you would see we have this block called the 6DOF block, which calculates your robot 6DOF state given the input forces and moments. So if you look here, you see the forces and moments coming in from a model, and then there's this tick stop block that's going to calculate your states like velocity, position, um, acceleration, and all that stuff, which then goes into a bus, which is a way to like group all these signals together into a signal line, and then that comes out as the UAV state. Now, the forces and the moments, you probably know the forces that are acting on the drone. It's going to be environment forces like gravity, lift, and any force due to high winds. And then you also have the forces from the propellers itself. I'm using an Euler angle representation of the six-half equations, but we also have quaternions if that's what you like to use. And as I said, the UAV has a high fidelity plant model, but then if you want to focus more on, for example, just the detection of the landing zone, you can replace this with a lower fidelity model and focus more on LiDAR processing and kind of like pick your battles on what you want to simulate, what you want to refine, and then once you're happy with that, you can always go back to a higher fidelity model and keep iterating on these fidelity levels so as to get a more real life solution as you go towards the end. The idea is that when you start kind of simple, but you know, um, complex enough to capture the dynamics, but not too much getting into the nitty gritty of the dynamics. You want to get a working model as soon as you can, and then you choose which one to refine, right? So if LiDAR processing is your focus for the week, then you're going to focus on getting really good LiDAR data, trying to see how you can filter that and then segment that landing zone. And then once you have that, you can then add like more dynamics into your quadcopter. So now the LiDAR is going to be shaking more because the dynamics is more there's more fidelity to your dynamics and there's going to be more noise. And then you can test how your algorithm holds up to that new dynamics of the platform of the drone. So that's typically how like model-based design works. You have like a simple model and then you work on making it more complex so that by the end of your project you're like have a pretty good model of your whole system and then it'll be easier to translate from simulation to hardware. And for the ship, like I said, we have a simple model. We have a forward velocity that you can see here, and then we have some rocking motion that's modeled by like sine waves, so you can see it rocking in the roll axis. So it's going to roll a little bit, and then we also have like more ways you can improve the fidelity of this model, like that's shown here. But that's up to you when you want to do that. For this webinar, it's going to be a simple ship model. All right, so let's talk about the algorithm itself to land. The first part is, of course, perception, where you have the drone with the LiDAR attached at the bottom of it. And now we're going to use those points that the LiDAR returns to figure out where to land, right? So there are like a lot of things that you want to do in the perception part. For example, you need to filter out like the water surface and focus on the ship or like on a boat. And then on the boat, you want to figure out what is the landing surface. Since this is a flat surface, you can use some ground extraction methods to figure out which area is likely to be the landing zone, and then go from there. Once you have that, you need to have a planning submodule that kind of plans the path from your robots or like your drone's current position to the landing position that was determined by the LiDAR processing. And once you have the path, you're going to have some kind of controls to get the drone to follow that path, right? So essentially, what kind of signals do you need to give to each rotor so that it can follow the path as closely as possible? So let's go into each step in a little bit more detail. For example, we have the algorithm for perception, right? We have four steps that you can see here. We have the read point clouds, which you will get from your simulation model. And then these point clouds, you can configure them based on whatever LiDAR you're using actually for your robot. So you can see we have like Velodyne, Rooster. And then we also have like some more that are not mentioned here. But the idea is that you will be able to configure the LiDAR depending on what LiDAR you're going to use in the real world. And once you have those point cloud data, you're going to do some kind of filtering to like remove the sea and focus more on the ship. There are some methods here like plane fitting or SMRF, or you can even use AI if that's what you want to do. And then once you have that, then you want to detect the ship. Again, you can do clustering or AI-based segmentation to detect the ship. And then finally, once you have the ship, you want to detect the landing zone. And for a known zone, you can use like, region of interest based methods. For example, for at least at RobotX, you kind of know your landing zone dimensions, right? You built the boat, you also know how much space is available for the drone to land. And if you have a platform on top of it, then you know the dimensions of the platform. You can use that information in your landing zone detection algorithm because you're going to get the 3D world points from the LiDAR, right? And then you can fit a plane that matches the specification of your landing zone to try to figure out where the zone is. Knowing that is makes it a little bit easier to detect. But if you're trying to land in like unknown terrain, then we also have some algorithms there um, that you can find in the MathWorks documentation. But for this part, the focus is going to be on assuming that you know the specification of the landing area, and we can use that to kind of detect the zone more accurately. So the first part is going to be like segmenting seawater from or like a river or a pool or any environment that you're in. You want to take out the water from the ship, right? And we can use some kind of filtering algorithms for it. That there are like different ways you could do it. Segment ground SMRF is the one that we are going to be using, and then we are going to extract a large cluster of points. Again, this works because in this example, I have only one boat. So I'm just going to look for a large cluster of points. I'm going to assume that is my boat, right? If you have more, for example, if you have more boats, which you might have in a competition environment, in that case, the drone needs to know your boat's location or like a rough estimate of where your boat's going to be located which I assume it would because your drone would be ideally communicating with the boat, and you're probably sending some GPS value from the boat to the drone or vice versa, and you can use that to kind of look at cluster of points in that particular region or direction. And then you can the way we detect ship from the water can also be based on intensity. A lot of lidars now return intensity values. So when you have something very reflective, that's going to have more intensity value. You can use that to detect, for example, a ship, right? A water is not going to be as reflective because it's going to absorb a lot of the laser scans, and whatever is coming back is going to be very low in intensity. Um, so you can use the physics of that materials around you to kind of identify and isolate the object that you want to focus on. Yeah, so I already went through this. We're gonna use the information that you know the size of the landing area, and then you will use that to find the location on the ship. And then if there is no landing zone detected, then we'll use the last detected zone as the target position to reach. Now, coming to planning and decision making, we are going to use the waypoint follower block that takes in, a look ahead point, the desired course, desired yaw, and the cross-track error. Then outputs like, um, sorry, it takes in the UAV's pose and then the set of waypoints, and then outputs the desired yaw, desired course, and the look ahead point. So you can use that. That would then feed into your control loop. So you have the reference values coming into your control loop, and then the your drone's pose would be the actual value, as you can see here. So we have like three different controllers. We have a position, attitude, and yaw control, which then goes into a control mixer that outputs thrust values to the rotors. Here, I'm using PID controls for all of these. For this application, PID works pretty well. But if you want to do more like disturbance rejection or stuff like when there's like high winds, right? You might want to look into more complex controllers. PID can still work if it's tuned really well. You can also have like cascaded filters, or you can cascaded controllers, or you can look at more optimal controls if that's useful for you. All right, now let me switch to Simulink, and then so I can show you how all of these fit together. Are there any questions, Alicia?
There are. We have a couple of questions. So one of them is, how do you decide the right level of fidelity for the plant model? At what point does a higher fidelity model stop improving controller performance enough to justify the added complexity?
Um, that's a great question. So the rule of thumb is always start simple, get a working model first, right? So for example, if you have um, a drone model that, for example, the one that I showed in the presentation, that has decent fidelity. It has a lot of the physics going on, and it's kind of um, accurate for the drone dynamics. But then, like I said, if you want to focus more on actually the LiDAR processing, then you don't need as much drone fidelity. So you can reduce on that and then focus more on this part where it's processing the LiDAR data. So it depends on what you're trying to achieve first. But then increasing the fidelity comes after you've kind of achieved your main objective, right? Like for example, the main objective is to figure out how to use the LiDAR data to extract the landing zone location, right? And then adding more fidelity to the drone just makes it so that the LiDAR values that come to you is going to be more shaky or more complex to analyze than like a simple static LiDAR scan. And so that again helps you refine your earlier algorithm. So you want to go ahead and make that make the drone model higher fidelity. And then you keep doing that till you've reached a place where you're happy with your algorithm's performance. There is a line where adding more fidelity doesn't help your progress. That is something that can only be determined based on application. As a rule of thumb, I would say get to a good place where the drone and any systems dynamics has been reasonably captured, but maybe you don't want to do all the nitty-gritties of it. For example, maybe it has an odd shape and you're trying to like get the inertia or get like drag coefficients for that particular shape. So those things, maybe you don't have to go into that much detail. You can scale back and then kind of reduced fidelity on that sense, but you also don't want to make it too simple, like which would not help you with your main objective, which is to use that LiDAR data. So it's up to you really, but I would say start simple and keep adding complexity, and then once you're happy with it, you can like continue to keep adding it. But at some point, you're going to have your Simulink model or any other simulation software that you're using, it's going to slow down a lot because it's going to do a lot of computes based on how complex your model is. So that's when that's like your natural stop, right? You don't want to do more because your PC or your system is struggling with all this added complexity.
We've got a couple more questions. Do you want them now or do you want to hold them until a little bit later?
Okay, you can hold them a little bit later.
Perfect.
I'll
Yeah.
just go with the Simulink model real quick, and then we can take some more questions. All right, so if you had been in my first webinar, I showed you a little bit about what we use for simulation. We use Unreal Engine at the background. That's what we use for the RoboSub simulation environment, and that's what I'm using for this as well. This was actually built by a colleague of mine, so I should give him credit. But um, we use Unreal Engine for all the simulation, like the 3D visualization that you see in this. And then we also have like sensors that come with these visualization environment. For example, I have the simulation 3D LiDAR. And then if you remember earlier when I was talking about the LiDAR, I told you you can choose a LiDAR that matches the actual LiDAR you would use in your application. And you can do that by opening this LiDAR block. And if you go to parameters, you can set the range of your LiDAR, the vertical and angular resolution, and the field of view to match the data sheet of the LiDAR that you use, right? That way you get a data that is more reflective of what you would get in the actual field. And then you have a mounting tab where you determine how the LiDAR is mounted to your robot. So you give it like, translation and rotation, which, if you do a lot of work with URDF, you know how this works, how the LiDAR is mounted with respect to the origin of your robot. And then since it's a simulation, you can also output the ground truth value. So, for example, in Unreal Engine, each object or each actor has a tag or an ID associated with it. And when you have like a camera or a LiDAR, you can set the LiDAR to output ground truth, which would then output the tag or the ID of the object that the laser beam has hit. Right. So if you get like 100 points, then you know from where each point reflected back. You can get that information. This is super useful, but this is usually only in simulation. You don't get that much detail in real world data unless you have trained some AI model to like detect objects based on the point clouds, right? But in simulation, you can use that information to kind of focus more on the algorithm itself, on like figuring out the area, and then you can see how that works when you don't have that information. And then similarly for a camera, you can like output what each pixel represents. So, it's like a semantic segmentation map that you get from a simulation camera as well. So I have this LiDAR. It's going to be mounted on the drone, and we're going to take all this information and then what what's happening here is basically we're adding noise to the LiDAR value, right? It's not going to be clean in the real world. We need some noise. So that's what is happening here. I'm going to use the labels, which is the ground truth data, to get the ship and the water, and use that to determine how I want that noise signal to be. Um, but the labels are not going to be used in the actual detection part. It's just used to add noise to the LiDAR value. So now we can see that you get a noisy point cloud, noisy reflectivity data, and then some translation rotation, which then goes into your LZ detect function, which is the landing zone detect function. And this is going to use some of the algorithms that I showed in the slide. I don't want to go over line by line because that's too boring. But what we do basically is filter out the water data, then try to find a flat surface based on the dimensions that we already know for that landing zone. And then that information is going to go to your UAV planning and control, which will then output the state, which is used to simulate the drone landing. And then we have a visualizer to visualize the point cloud. So that's the LiDAR modeling part. Again, if you're interested in the exact documents or the exact function that's being used here, you can always send an email to roboticsarena@mathworks.com, and then we can give you the details of it. But for the sake of time, I'm not going to go into every detail on the functions. But I hope you get the gist of what we're trying to do in this part of the model. And then in simulation and control, we have a plant model. So if I go here, this is a reference model. I'm not sure if you guys are aware of what a reference model is, but basically reference model is when you have a separate model, that separate Simulink model, and you're using that in a different Simulink model, right? So this is multi-rotor landing only one. And then if you see here, I have a separate .slx file for that model alone. So if I open it, it'll be like the same thing. But then when you use it as a reference model, that's just going to be compiled and run a little bit more faster than having to model this completely here. So you can kind of like use that as a library of sorts to just pull it in and then use it to simulate other aspects of your model. So we're going to use this reference model and take in the waypoint or like the landing zone that you want to get to. And this would then go into your guidance state flow. So you're getting your pose and the waypoint into your guidance state flow, which will then determine like your state, right? If I go in here, you can see we have like a bunch of functions. There's a landing function, and then there's a guidance logic. And we like I showed in the presentation, we're using a waypoint follower to get the inner loop commands from the waypoint and the pose of the drone. And then once we get to a descent zone, we can change it a little bit so that the waypoints now go like straight down, so it's easy to get the drone to land. And that's your kind of your guidance loop. And then you have the commands that go into your control system, which will then output thrust commands, which again, the same subsystem that I showed you before. We have a PID control that's going to control your position, yaw, and attitude. And then it's going to go into like a motor mixer that will then output like all the thrust values for each thruster, which will then determine the plat, which then goes into the UAV plant model. And you're going to use thrusters, forces, and moments, and you're going to use environment forces and moments to determine how your simulation drone would move, and use that as the loop to again do the cycle. So once that is updated, again the LiDAR values will change, and the same process continues. And when we come to the ship, again, like I mentioned, it's going to be super simple. We have a forward velocity. It's being integrated to get the position, and there's no y velocity. It's just moving in the search direction. And then we have some rolling action that's going to go into the ship as well. Yeah, now I can take some questions before I start simulating the model.
Absolutely. We've got a few more questions. So another question we had from earlier on was, how does the system handle partial occlusion of the ship or landing zone, such as if the deck isn't fully visible in the point cloud?
Yeah, so right now, this one doesn't handle partial occlusion because it's a simulated environment and we haven't modeled that, but you can do it. You can have like partial occlusion. You can like in this function that adds noise, you can basically kind of neglect a bunch of point clouds so that the output that goes into your LZ detect or the landing zone detect function has partially occluded data. And they're like different ways you can kind of account for that. partial detect is kind of a tricky problem because you don't know how much of the landing zone is going to be visible. So the first step is always to detect the ship, right? Once you have the ship, you one of the fallback could be like you kind of navigate towards the ship and hoping that the lidar values get better as you get closer to the boat or the ship that you're trying to land in. That could be like a fallback behavior that you can model in your state flow or any logic that you have, and that usually helps a lot. Other issues when there's a lot of visibility stuff that you can't really detect. Visibility in the sense you have a lot of things flying over the drone itself. Maybe you have some flag or something that's kind of causing it, and in that case, no matter how close you are, you're going to have some kind of occlusion. So you're going to have some kind of a clustering algorithm that doesn't try to get the maximum data, try to get a possible landing location that you can use. Again, actually, let me drop this in the chat so you can go over some of the algorithms that we have when you don't know where you want to land. Yeah. Alicia, if you can share that, that'd be great. Uh,
Absolutely. Do.
so yeah, so partial occlusion, basically you just have a fail safe where if you can detect the ship, you try to go closer to the ship to figure out a better landing zone. If not, you use some other clustering algorithms to figure out where to land. But great question. Thank you.
Two more questions. I can
Yeah.
throw at least one of them
Mhm.
out. So one of them was, have you found PID to be sufficient for most of these autonomy tasks, or do you ever need to move to another control method like MPC?
Um, I'm a big fan of PID. PID for the most case just works. It's like it, MPC is great, but then you have like a lot more that you want to do. You have to do to get the MPC to up and running, right? It's not as straightforward as a PID, but also PID is kind of robust. You don't really have to worry about whether PID would work. For the most part, it works. I would say about 80% of control problems probably use some form of PID, whether it's like cascaded or like multiple PID loops or something like that. For the most part, it works, so I'm a big fan of it. But um, obviously, there's like way more advantages you get if when you use an optimal control like MPC, right? There's there's like pros and cons. Well, the pro is that you get a much better controller for your system, and it's like a multiple input, multiple output control system. So it's like really good. But the cons is that it's not as simple as a PID to implement. So you need to know more to like model it. A lot of things that you need to model to get the MPC to work, and also implementation wise, it could be a little slower depending on your horizon that you choose. So that is like the pros and cons of it. You gotta weigh it. For most part, PID works. MPC really excels if you have like a lot of noise and a lot of for example, a lot of wind, and you're trying to account for that. In that case, MPC might be a better choice. But yeah, it's up to you, really.
And then our last question was, are you doing most of the point cloud processing on board in real time?
Yes, all the point cloud processing is happening in these functions here while the simulation is taking place. So you can see when I run the simulation, you can see the LiDAR data changing, and then it's trying to detect the landing zone at each time step. And again, once you have the data, you can always convert this into Or you can always generate C++ code or GPU code out of it that you can run on your Jetson or on your Raspberry Pi, or probably not Raspberry Pi. You can run that in your controller, so you don't have to, hand translate it into Python or C++ again. The cool thing about LiDAR processing is also that, as I mentioned, we support GPU code generation, so you can really speed the LiDAR processing part to match the rate at which you get points from your LiDAR. All right, if that is the last question, I can go ahead and show you the simulation. One thing is I want to set the camera angle a little bit higher. So you can see that I have the stop time set to infinity, but then I have a stop sign, as you can see here, that will stop the simulation once I know that it has landed, right? Once I know that the drone has landed on the landing zone. Oh, there you go. Did I rotate it? Oh yeah. The LiDAR was loading. You can see the drone flying away, trying to head to the ship. And let me pull LiDAR data. It's still loading. Oops. What happened to LiDAR visualization? Let me run this one more time to see if I can get the LiDAR to show up. The point cloud to show up. This is the reason I recorded, because I know when I try to show it won't. That is weird. I'm not able to see the point cloud data. Okay, so I'm gonna go back to the video just to show how it looks like. I'm sorry about that, but I don't know why it didn't work. But this is how it's supposed to be, right? You have the drone, and then you would see um, the LiDAR value, the point cloud value is being put here, and then the yellow part here is the detection. That's the highlighted region where it's trying to land. And then you can see how it shifts and rocks depending on how the boat or the drone is moving. And you like sometimes you don't like when it's blue you don't really get the detection, but when it's yellow you get it. Um, Let me just go back. So here in this frame, you can see that the detection zone is kind of blue, and it hasn't, like the algorithm didn't really fit that plane in that particular frame. So it's going to take the last known position in this case. But as as you play it forward, then there'll be like a frame where it will detect it. For example, now it detects it, and then it keeps going to that new spot. Yeah. Uh, presentation. Yeah, so I'm not sure why the LiDAR didn't show up, but that's how it's supposed to look like. And in simulation, you can also, so this is like LiDAR-based data. If you want, you could also use a camera-based environment, right? For adding a camera, it's pretty simple. You just search for a camera. You have like a simulation 3D camera right here. There are like multiple ones. You choose any of them really. And this would be a camera that is placed. You want to go there and then tell it where to place the camera. You don't want it on the ship. You want it on the drone. And then you can always set the camera parameters depending on the camera that you're actually using. And again, like I said, you can output semantic data, semantic segmentation data, if you're trying to use this for um, training a deep learning model, right? You can use ground truth data, and you can have the data from from the raw sensor data and use that to train a deep learning model to detect the ship if you're using a camera-based approach. So let me add the camera. Maybe I'll give it an offset of I don't know, 8 centimeters above the maybe 10 centimeters above. Um, and then I can add a video viewer to see the output of that camera. This is a little GPU heavy because you're processing LiDAR, water, and all that stuff. Uh, what is it? See? Okay, I think in this case, the camera is in a weird location. It's not able to get the right image. Uh, Stop that. Uh, the cool thing is that you can also visualize the field of view of your camera. So I'll use that to see where the LiDAR is placed. So I know like I'm not placing it in a weird location. Hmm. Okay. I am not able to see the field of view. All right. I don't know. Today my PC is acting up. It doesn't show anything that I wanted to show. But I will go back. Okay, stop this model. Yeah, this my PC doesn't have a GPU, so it's been like I am really pushing it to the limits to try to get this to simulate. But if you have a GPU machine, it is much more smoother and can show like a lot more of the data, and hopefully it'll be much better than what I just showed. But that's essentially what I'm trying to show here. Is that with simulation you can always add more sensors, find different ways to solve the problem. Because while your hardware team is busy building your systems that's required, and that way you can really make use of all the time to have a solution before you have all the hardware ready for the competition. Go back. Oops. Alicia, is there any more questions? Oh, I
Yeah.
did see that comment. Yeah, it doesn't run when I want it to. Yeah, it has followed me from my competition days. It just doesn't happen when I have to present it to someone.
They are we've got some folks commenting in our chat right now, the understanding of what it's like when technology doesn't work the way we want to. So relating to you,
Thank you,
Abhishek.
guys.
Some
You
shout
know
outs
how
for you.
this is.
We've
Yeah,
got
I
some
have
shout
judged
outs
a few
for you.
competitions, so I
Yeah,
know it happens way more than I would like it to.
exactly. It happens to the best of us. But we had one question in there in
Mhm.
and amongst our fun chat. And I will say we also had some shout outs for you as well as for being a good judge. But one question was, how often is the control loop actually updating based on the LiDAR data?
Um, so this for this model, the sample time is set to I think it's 0.1. So it's like 10 times a second, I believe, because the lidar outputs values at 10 hertz. So you're gonna get every, you know 10 times a second, you're gonna get a new feed. But then you can have like great transitions to have a control loop that's running at a faster speed, or ideally, 0.1 is already pretty slow. You don't want to make it much slower, but yeah, you can adapt it based on whatever lidar you use. All right. If there are no more questions, I want to talk about some of the MathWorks award we have for this year. This year we have three awards. We have it for RoboSub, SUAS, and RobotX. Um, RobotX, you probably, if you competed before, we had the same award a couple of years ago too. It's going to be the same if you use MATLAB or Simulink for any part of your design of either your submarine or your boat or your drone, since we have like everything. Um, you can apply for this award. Just tell us how you used MATLAB or Simulink to solve whatever problem you were facing, and then we'll judge you, and then we'll provide you an award based on that. And that's the same for SUAS as well. It's going to be based on how you use MATLAB and Simulink. What kind of problem did our tools help you solve? We want to know that basically, and then we want to know how easy or hard it was to use our tools and what improvements that we can make to make it better. And then for RoboSub, this year we have this simulation environment that you see on the left. We have an underwater environment that kind of models your submarine, the RoboSub environment. And the idea is to have a simulation challenge so you can do all the tasks that you would do at RoboSub in this environment. And hopefully you'll then be like more prepared for the competition and have more confidence on your algorithms and solution. All the awards have prizes worth up to $2,000. And as I said, RoboSub is a new virtual competition, and the RobotX and SUAs has the MathWorks Design Award. And we're going to have more details soon-ish for RoboSub. I know RoboSub's coming up. It's only 2 months away, so we're going to have it out in probably a week or two. That should give you 2 months to like submit a simulation solution. And I hope you guys gain value out of it, and hopefully also some money by participating in this challenge. But that's all I had for you today. If you have any questions, always feel free to email us at roboticsarena@mathworks.com. You can also reach out to me in Discord, or you can send out an email. I put the group email because on days when I'm not in office, it's easy for someone else to respond to that question. But I'm always reachable on Discord if you're in the RoboNation server. And you can always even let Alicia or someone in RoboNation know, and they can get back to me as well. Thank you.
Thank you so much, Abhishek. Like you mentioned, please reach out to his team. Make sure you reach out to RoboNation. We're competitions@robonation.org. If you've got any questions, if you joined us today or are joining us in the future at a later date and are curious about what RoboSub is, what RobotX is, what SUAS is, we'd love to tell you more about it. If you'd love to start a team, we'd be super excited to get you all the information you need to be a part of the RoboNation community. To those of you who are listening, I know we've got some sub teams, I think, that are represented here in our chat tonight. Make sure you participate in that simulation award. It is a great opportunity for you to flex your skills in the communications department, but also showcase how you're using technology and get to know one of our amazing partners better. It's just great resume building opportunity and just more chances for your team to be seen across our various competitions. So thank you to those of you who joined us. Thank you to those of you who will be joining us in the future to watch this. But the biggest thank you to Abhishek and the MathWorks team for making this possible and for their continued support of each and every one of our programs. And what that means is their support of each and every one of you as our students. So we look forward to having Abhishek on our various competitions throughout the summer and into the fall. For those of you coming to the IGVC competition, you will see him in June, and we'll also have him on site for RoboSub. And heading into later in the year, we've got SUAS and RobotX, where we'll be very excited to bring our MathWorks friends over. So please give a big shout out to him. And if you've got questions, make sure to send them his way. So thank you for joining us tonight. We will see you for our next mini series session in 2027. But in the meantime, stay engaged with our RoboNation community, visit us on social media, and make sure you follow MATLAB students as well. Thank you.
Awesome.